Welcome dear students. In the previous session, we discussed about the refraction of plane wavefront at denser medium. That means refraction of plane wavefront when it travels from rarer to denser medium. But in this session, we discuss about the refraction of plane wavefront when it travels from denser medium to rarer medium. When a ray of light, here we consider wavefront, not wave. Okay, when plane wavefront, light travels from rarer medium to denser medium, its velocity goes on decreases. That is, v1 is greater than v2. But here, the light ray travels from denser to rarer medium. When it travels from denser to rarer medium, its velocity goes on decreases. When light travels from denser to rarer medium, its velocity goes on decreases. That is, v2 is greater than v1. When light ray travels from denser to rarer medium, its velocity increases. That is, v1 is less than v2. Okay. So for that, let's draw an interface. That is, let you call this interface as P dash. When a ray of light incident on the interface of two medium, this is our incident ray. Let's draw a normal here. So this is the angle of incidence I. In ray optics, we discuss about refraction of light. That when light ray travels from one medium to another medium, it undergoes refraction. If its velocity increases, it bends away from the normal. If its velocity decreases, it's bent towards the normal. Here, the first medium is denser medium. Medium 1 is denser and medium 2 is rarer medium. Here the light travels from denser to rarer medium. When it travels from denser to rarer medium, its velocity goes on increases. Here v1 is the velocity of the first medium and v2 is the velocity of the second medium. It travels from denser to rarer medium, its velocity goes on increases. That is, v2 is greater than v1. Okay, in the refraction of plane wave at a denser medium, v1 is greater than v2. But here v2 is greater than v1. So if v2 is greater than v1, that means its velocity goes on increases. As a result of this, the refracted ray bends away from the normal. Okay, so this is the angle of refraction. But in this chapter, we consider wavefront. So let's draw the wavefront for this. So, by parallel beam of light incident on the wavefront. Parallel beam of light means it is we will get a plane wavefront for that. So this is a parallel beam. So let you draw your plane wavefront. Let you call this as AB. So here AB is our incident wavefront. Okay. So this is the angle of incidence. So when this wavefront incident on this interface, what happens? It undergoes refraction. According to the Huygens first principle, each point on the wavefront is a source of secondary disturbance called secondary wavelets. That means small waves are emitted. So suppose if we draw a tangent for that ray, that small wavelets, you will get a secondary wavefront. That is the Huygens second principle. So the AB is incident ray. Then for this, if we consider only one arc, okay, one arc is enough. So this is the small wavelet emitted by the primary wavefront. Okay. Suppose if we draw a tangent for this, you will get. You extend this. Suppose if we draw a tangent for this, we will get a wavefront like this. This is our refracted wavefront, CE. Carefully you observe that the BC is greater than A. In the previous case, BC is less than A. BC is less than A. Here in the previous case, BC is greater than AE, but in this case BC is less than AE because here the velocity of the light increases because this is the rarer medium. medium. So at the same interval of time tau, the distances BC and AE are travelled. But for the same time BC here, for the same time interval BC is less than AE. So C is the refracted ray. From the figure, AB is the incident wavefront, C is the refracted wavefront. So this is the angle of refraction R. Okay. So from the figure, what is AB? AB is AB is the incident wavefront. Incident wavefront. Okay. Next. CE, what is CVE? CE is the refracted wavefront. Refracted wavefront. Okay. What is I? I is the angle of incidence. Angle of incidence. What is R? R is the angle of refraction. Angle of refraction. Okay. Then here in the previous case I is greater than R, but in this case I is less than R. Angle of incidence is less than R because V2, since V2 is greater than V1, velocity of the first medium is less than velocity of the second medium, or velocity of the second medium is greater than the velocity of first medium. Therefore, angle of incidence is less than angle of refraction. So, the distance travelled BC is given, the velocity are different. This is the velocity of the first medium and this is the velocity of the second medium. So, velocity of the first medium, the velocity to travel distance BC is given by V1 is equal to velocity is distance by time. This distance is BC. So time interval is tau. Again the velocity of the second medium is V2 is equal to again distance by time. Distance is AE. So the distance AE and BC are travelled in the same interval of time tau. So distance by time is tau. So V1 is equal to BC by tau and V2 is equal to AE by tau, which implies BC is equal to V1 tau and AE is equal to V2 tau. Okay. Next, from the triangle ABC. From triangle ABC, sin I is equal to opposite by hypotenuse. For this ABC, opposite side is BC, hypotenuse side is AB. So sin I is equal to BC by AC. Similarly, from triangle AEC, sin R is again opposite by hypotenuse. For this, opposite side is CE and hypotenuse side is AC. So sin R is equal to AE by AC. So now we divide this by this. So I'll get sin I by sin R is equal to BC by AC. That whole divided by AE by AC. So AC get cancelled. Remaining is sin I by sin R is equal to BC by AE. Now substitute the value of BC and AE. You get sin I by sin R is equal to BC is V1 into tau and AE is V2 into tau. So tau will cancel. Remaining is sin I by sin R is equal to V1 by V2. But we know the relation between the velocity and the refractive index, that is V1 by V2 is equal to N2 by N1, where N1 is the refractive index of the first medium, N2 is the refractive index of the second medium. So I will get sin I by sin R is equal to N2 by N1, or this can be written as N21, refractive index of second medium with respect to first medium. So this proves the Snell's law. That means we can prove the Snell's law by using Huygens principle. Okay, so sin I by sin r is equal to n2 by n1. Here we observe a special case. Here we observe a special case, that is, if I is equal to IC. If I is equal to IC. What is IC? IC is the critical angle. In ray optics we define the critical angle. What is critical angle? It is the angle of incidence for which angle of refraction becomes 90 degree. It is the angle of incidence for which angle of refraction becomes 90 degree. If I is equal to IC, then R is equal to 90 degree. Angle of refraction becomes 90 degree. That is, if I equals IC, then R is equal to 90 degree. After this, that means if I is greater than IC, if angle of incidence is greater than the critical angle, it undergoes total internal reflection instead of refraction. Please note this. When I is greater than IC, the incident ray undergoes total internal reflection instead of refraction. So if I is greater than IC, then the incident ray undergoes total internal refraction. That is, total internal reflection. That one is very important. You know the condition for total internal reflection in the ray optics, that is, when ray of light must travel from denser to rarer medium. That is first condition, and second condition is I is greater than IC. Here also, if I is greater than IC, that undergoes total internal reflection. That means all the ray of light, if angle is greater than is the critical angle, all the rays undergoes reflection instead of refraction. Okay. Now we shall derive law of reflection by using Huygens principle. What is reflection? Reflection is the bouncing back of ray of light. Okay. So law of reflection, the first law states that angle of incidence is equal to angle of reflection. Now we prove this by using Huygens principle. Okay. So in the ray optics, we know the reflection concept. Suppose let's draw a reflecting surface. Okay. When ray of light incident here, when a ray of light incident, let's draw a normal here. This is the angle of incidence, that is the angle between the incident ray and normal. So it undergoes reflection, that is bouncing back of ray of light. It undergoes reflection like this. So this is the angle of reflection. So this is the case of ray optics that we consider light as ray. But here we consider light as wave. That means we draw wavefront instead of waves. Okay. So wavefront is nothing but locus of all the points which oscillates with the same phase. Suppose when wavefront incident on light, incident on interface means bunch of waves incident like this. That means number of waves are incident like this. Okay. Now we mark the locus of same point which oscillates with same phase. Then join this point, we will get a wavefront. What is that wavefront? Plane wavefront. Here we get the plane wavefront. Because the parallel light from an infrared source or parallel beam of light gives plane wavefront. So this is the incident wavefront for this. Okay. So this what happens when these rays are incident on the interface of the two incident on the reflecting surface, it gets reflected like this. It gets reflected like this. Like this. Again you mark the locus of same point and join this point. We'll get another wavefront that we called as reflected wavefront. This is our reflected wavefront. Now I think you get a clear idea for the incident, to draw the incident wavefront and reflected wavefront. Not necessary to draw all the waves, just to write This is the incident wavefront and this one is the reflected wavefront. Okay. So this is a rough idea for you. Now we draw a clear picture for this. So this is the reflecting surface. You call this reflecting surface as M, N. Okay. When a parallel beam of light incident here like this. So let me draw a normal for this. So this is the angle of incidence. Normal line is a straight perpendicular line. So this is the angle of incidence I. Okay. So this ray angle goes. This ray angle goes reflection like this. This is the angle of reflection. This is in the case of ray optics. Now we shall draw a plane wavefront, incident wavefront. Where you have to draw a plane wavefront, incident wavefront? Here or here. Now we draw an incident wavefront from here. Like this. So let you call this point as A, this point as B. So this is the incident wavefront. For this incident wavefront, you will get plane wavefront, reflected plane wavefront here. You will get reflected plane wavefront. How do you get this plane wavefront? When when a wavefront is incident on the reflecting surface, what happens? According to Huygens' first principle, each point on the wavefront is the source of secondary disturbance called secondary wavelets. That means secondary wavelets are formed. Suppose if you draw a common tangent for the secondary wavelets, you will get tangential surface. That tangential surface itself forms a reflecting surface. Okay. Let us call this point as A, B, C and this as E. Okay. So here AB is the incident wavefront and CE is the reflected wavefront. AB is the incident wavefront and CE is the reflected wavefront. Okay. So we draw according to Huygens' first principle. When the plane wavefront is incident on the reflecting surface, what happens? Each point on the wavefront is the source of secondary disturbance called secondary wavelets. That means small waves are formed here. Suppose if we draw a common tangent for this, we will get a plane wavefront. That wavefront is known as reflected wavefront. So it is not necessary to draw all these spherical wavefront. Just we draw an arc. Okay, so this is the tangent of this. Okay, so this is the tangent line. This is the reflected wavefront. So is the angle of incidence, R is the angle of reflection. Student, please note this. Here the distance AE and BC are same. They travel same distance in same interval of time because here the medium does not change. But in the previous case we discussed about the refraction of light. In refraction, light travels from one medium to another medium. Its velocity goes on, increases or decreases. So the distance traveled in the same time also increases or decreases. But in this case, the light ray travels only in one medium. That means velocity remains same. So that is V is the velocity of the medium. So therefore, at the same interval of time t, the distance AE and BC are same. Okay. AB is the incident wavefront. AB is the incident wavefront. CE is the reflected wavefront. Reflected wavefront. I is the angle of incidence, R is the angle of reflection, and V is the velocity of light in the medium. Velocity of light in the given medium. And tau is the time taken by the light, to travel distance from B to C and A to E. Therefore, B is equal to distance by time, that is BC by tau. Will get BC is equal to V into tau. And similarly, velocity V is equal to AE by tau, distance traveled by time, that is AE by tau. So AE is equal to V into tau. Here we does not take V1 and V2 because the light travels in the same medium. So V is equal to BC into tau and V is equal to A into tau, which implies BC is equal to V into tau and A is equal to V into tau. That means from these two equations it is clear that BC is equal to AE. The distance travelled from B to C is equal to distance travelled from A to E at the same interval of time tau. Okay. Therefore, from the two triangles, here we have two triangles, that is ABC and AEC. The two triangles ABC and AEC are congruent. If two triangles are congruent, then their angles are same. That is, angle of incidence is equal to angle of reflection. That is, I is equal to two triangles of congruence. Then I is equal to R. That is, what is I? I is the angle of incidence. That is R is the angle of reflection. Therefore, I is equal to R. This proves the law of reflection. What is the law of reflection? Angle of incidence is equal to angle of reflection. Here we prove this law of reflection by using Huygens principle. Okay.